So this here, we'll look at two different sort of standard scenarios where we got different currents that are creating magnetic field at some location, and we want to know the total amount of magnetic field. Because a magnetic field is a vector, which means that we can add up the total size of the magnetic field by adding up the contributions from all of the individual sources of magnetic field. So first we'll look at this scenario here. And it basically, just imagine an infinite wire going up and it's creating magnetic field, but at this point right here, it goes at the moment just in one little loop and then comes up again. So this is the same as me saying that I have an infinite wire that has current and is creating magnetic field, and I have a single loop sitting there that is also creating magnetic field. Now, one more thing to note about magnetic fields here so we can keep our directions straight is that we're going to assume that if the magnetic field is pointing into the wall, then it's going to be negative, and if it's pointing out of the wall, it's going to be positive. So, with that said, we can first ask, okay, so what is the size of the magnetic field at this point at the center of this circle due to the infinite line? Because remember, even if we ignore the existence of the circle for a second, we know that this infinite line of wires creating magnetic field all around the wire, and that means at this point in space there's going to be some amount of magnetic field pointed into the wall thanks to this wire. So, if we know this distance, at the moment we'll just indicate it as little r, then we know that the size of the magnetic field created by an infinite wire, a certain distance from the wire, is just given by this formula. And because we know that it's pointed into the wall, we're going to assign it the direction of being negative, negative pointing into the wall. Then we look at the loop and we say, hey, you know, the loop has a radius of r, you know, it's a nice circle, it's current's going around, it has a magnetic field in the center of a certain size. What is the size of that magnetic field? Well, it's just given by that formula. Constants, size of the current, and the radius of whatever the loop is. We want to check, we can say, okay, we'll follow around that loop. What direction does our thumb point? Points into the wall. Into the wall means negative, so therefore that part of the magnetic field is also negative. Then what we can do is we can put these two things together. But note, at the moment we have two different r's. One r refers to the radius of the circle, and the other r just refers to how far away that point is from the infinite wire. But note that because this is a circle, that means its radius, right, the distance from here to here and the distance from here to here are both just going to be the distance r. So that means this little r here, the distance away that we care about, is the same as just whatever the radius of the circle is. And so now we got a bunch of similar looking terms. We can pull out the negatives, the mu naughts, the i's, the r's, the 2's, and what we're left with is an extra factor here, 1 over pi plus 1. But really all this means is that here, right, this is the formula for just the size of the magnetic field at the center of a loop. And basically, thanks to that infinite wire being right there, that means it's making the magnetic field at the center of that loop larger because there's that extra magnetic field pointing that way. Now, there's one other thing we can do to this formula. When it comes to loops, we can envision that more than one loop sort of exists, sort of squished together. Now, this is different from the solenoid. We drew the solenoid and we said, you know, those loops extend over some region of space, and because they're extended over space, they create a nice uniform magnetic field in that center of those loops. What I'm saying here instead is, hey, you know, if I had a single loop, then it would create a magnetic field of a certain strength. But if I made two smush loops, then I create a stronger field that still has that, you know, is pouring out of here. If I did 3 loops, 4 loops, I'm creating a stronger and stronger field, namely at the point I care about, which is the center of the loop. So I can go up to this formula here, and if there's a certain amount of current flowing, but this thing came up and wrapped around only once, then this formula would be fine. But let's say it wrapped around n number of times. That means it came up and went around 1, 2, 3, 4, all the way up to n. Well, that means all I would have to do here is replace this I with, I should erase it, I times n. And that means this formula here just now gains the term n. So the size of the magnetic field at the center of this is going to grow with the number of extra times that wire loops around before it goes away and shoots off to infinity. So now we can determine the size of the magnetic field at the center of this configuration, the combination of potentially multiple loops of wire and the contribution from an infinite line of current that's also creating magnetic field here. Now, another scenario we can come across is, let's say we got two current carrying wires and they're running relative to each other. So in this case, here I got a current that's flowing off to the right, and here I have a current that's flowing off to the left. We'll still take the direction of into the board as being negative. So what's happening with these currents? Well, we use our right-hand rule to first figure out just some relative directions. This current here that's flowing this way, if I want to know the magnetic field it creates, it's creating magnetic field everywhere, but I run my thumb along the direction of that current, and then so this current here is creating out here magnetic field that's pointed out this way, and way over here it's creating magnetic field that points into the wall. This current, on the other hand, I run my thumb along this way, and so over here, currents or the magnetic field is going around this wire. So out here, that's creating magnetic field that's pointing into the wall, but down here it's creating magnetic field that points out of the wall. So this time, unlike before, where both of the different elements created magnetic field pointed in the same direction, namely into the wall, here, one of our things is creating magnetic field that points into the wall, and the other is creating magnetic field that points out of the wall. So we have to have different signs. Since we're just dealing with two infinite wires, this time we don't have to use this formula. We only have to use the formula that says, the size of the magnetic field is basically just based on your constants, size of the current, and how far you are away from the current carrying wire to the point you care about. So in this case, how far is each wire away? Well, this wire here, which is creating magnetic field that points into the page, and thus will require a negative, it's a distance of, notice here, the wires are spaced a distance L apart, and I care about a point that is an additional distance D away from this wire. That means the total distance from here all the way to here is going to be L plus D. Negative there to indicate that that contribution to the magnetic field points into the wall. This wire, it's only a distance D away from this. So in our formula, we only have to put distance D. And because the corresponding magnetic field points out of the wall, that means it's going to be positive. And so now, if we knew the size of the currents, we knew these spacings here, we could determine what the size of the magnetic field would be. And really, depending on those corresponding links and the sizes of the currents, this number might be positive, which would correspond to an overall magnetic field that points out of the wall, or it might be negative, corresponding to an overall magnetic field that points into the wall. It just really depends on how they're spaced and what the overall size of the two currents are, current 1 versus current 2. One other thing we could calculate related to this is, instead of just calculating whether or not we overall have a magnetic field pointing out to or into the page, we could also say, under what condition does the magnetic field, is the magnetic field zero? That is, this creates a magnetic field at this point, and this creates a magnetic field at this point, but they happen to exactly cancel out. Well, in that case, we would just set this expression equal to 0. Presumably, we'd have enough constants, or not constants, but enough variables known that we could then solve for some unknown. But really all we'd have to do is we'd have to set it equal to 0 if we say that the two are canceling out. Right? So those are our two examples of situations that we could set up. We could, of course, we can get crazy. We could add a circle of current down here that's also doing something. Because magnetic field is just a bunch of vectors, all we have to do is, as long as we know what the size of the vector is in its relative direction, we can just add them up with no issue.